Let's take a look at what it means to perform operations with functions. Specifically in this lesson, we'll look at what it means to add functions, subtract functions, and multiply functions. We won't look at dividing functions yet. We'll leave that for a little later. So to begin, let's say we had two functions, f at x and g at x. Let's think about what it means to add these two functions. In other words, what does f at x plus g at x actually mean? Well, to get an idea of what that means, let's consider the case where we have a specific x value, for example, 2. How would we do f at 2 plus g at 2? Well, that wouldn't be too bad. We could just evaluate the function f at 2 and evaluate the function g at 2 and add the two results. Now, what do we mean by evaluate the function f at 2? We really just mean substitute 2 into the function f and see what we get for the output value. So 2 is our x value, sub that in for x, and evaluate. You get a y value. That's f at 2. Similarly, we could evaluate g at 2 by substituting 2 for x in our function g. See what we get. That's our output or our y value. That's g at 2. We could just add those two output values together to get f at 2 plus g at 2. Now, a few things to think about with f at 2 plus g at 2. First of all, notice it's only the two output values that we're actually adding here. So when we do f at 2 and g at 2, what we get there are output values. We get an output value for f at 2, we get an output value for g at 2, and we add those two values. Furthermore, notice that we are adding the output values that correspond to a single input value. So if we substitute x with 2, for example, in f at x here, automatically this x becomes a 2 as well for g, because x and x here are the same variable. So when we change one of them, the other one changes too. And lastly, notice we can only perform this addition if 2 is actually in the domain of both f at x and g at x. So yeah, if we're trying to add f at 2 plus g at 2 here, you could only do that if it's actually possible to figure out f at 2 and figure out g at 2. If for some reason, for example, you could not find g at 2, there's some issue there when x is 2, there's no way you're going to be able to evaluate f at 2 plus g at 2 because you can't take care of this g at 2 part on its own. Okay, so to the point, when you add two functions, you're adding the two output values, that is the y values, for every valid input value. Okay, so when we want to add two functions, we're adding the y values for every valid input value, not just one, not just 2, like we did in the previous example where x was 2. We can add the two functions only where their domains overlap. Yeah, so when we were doing f at 2 plus g at 2, we could only do that if 2 was in the domain of both f and g. You can only add the two functions where they have overlapping x values or overlapping domains. And the same ideas apply to subtraction and multiplication of two functions. We did addition for our little discussion there, but you can do the same type of thing with subtraction and multiplication. So let's see some examples. We have two functions here, lists of ordered pairs. We have f, which consists of 5 points here, 5 ordered pairs, and we have g, which is also 5 ordered pairs. So how would we find f plus g? Let's take a look at our first point here. We have 1 for x and 2 for y in the function f, and we have 1 for x and 2 for y in the function g. Now, can we make an addition here? We can, because 1 is in the domain of both of these functions. So we have an x value of 1 here. So in our sum, we'll have an x value of 1. And what will the y value be? Well, it would be the sum of 2 and 2. We'd want to add 2 and 2, which is 4. So f at 1 plus g at 1 is 2 plus 2, which is 4. So the point 1, 4 is going to be in our result here. We can do the same for the next points. We have f at 2 and g at 2. So we have -3 and 5 for those values. We can add those together for an x value of 2, and that will give us a y value of 2. The point 2, 2 is in our result for f plus g. Similarly, f at 3 plus g at 3 would be 4 plus -6, so that's -2, so we'll have the point 3, -2. Now when we get to an x value of 4, we can't actually perform the sum because 4 is in the domain for g, but notice we don't have a point that has 4 for the x value in f. So 4 is not in the domain of f. So we cannot make that addition there, so we just move on, we skip it. We can add for an x value of 5. F at 5 plus g at 5 would be 8 plus 3, which is 11. So you'll have the point 5, 11. Notice we're not adding the x values, right? We're saying at the x value of 5, the sum of the output values is 11. So the point 5, 11 is in our result. And 6, -7 is a point for f, but notice in g here we do not have any point with an x value of 6. So we're not going to bother with that. We're not going to worry about that because 6 is not in the domain of g. So our result is this list of ordered pairs here. And we can do the same type of thing with subtraction. The only difference here is we would be subtracting the y values. So we'd have f minus g. So for example, for our first point, we'd have 1, and then the difference of these here is 0. So 2 minus 2 is 0, that is. So the point 1, 0 would be in our result. And you can see the other ones here. All we're doing is subtracting the two y values, the y value for f minus the y value for g. Now, do you think that g minus f would give us the same result as f minus g? Well, no, it would not, because, for example, if we look at the point where x is 2 in each of these, if we did f minus g, we have -3 minus 5, which of course is -8. If we do g minus f, we'd have to go the other way, 5 minus -3, which is +8. All right. So you're going to have the same look here, but all your y values are going to have the opposite sign because we're switching the order in which we subtract. So notice -8, +8, 10, -10, 5, -5. And last but not least, you can multiply as well. So if you do that, you'll be multiplying your y values for each valid x value here. And that's what you get. So, question for discussion, how does the domain of each of the results above compare to the domains of the original two functions? Well, notice the domain for all 4 of these results is 1, 2, 3, 5. And notice that 1, 2, 3, and 5 are part of the domains for both f and g. We see 1, 2, 3, and 5. And we see 1, 2, 3, and 5 with g. Okay, so the domain of these results is actually a subset of the domain of f and a subset of the domain of g. Okay, those x values are included in both f and g. Now we can do the same type of thing with equations. Suppose f at x equals 7x plus 5 and g at x is 9x minus 12. Let's find an equation for f at x minus g at x. Well, since we actually have expressions for f at x and g at x, if we want to find f at x minus g at x, we can just subtract those expressions, and that'll give us a nice equation for f at x minus g at x. Just when you do this here, don't forget you're going to be subtracting 9x and you're going to be subtracting -12, so that ends up usually being written as plus 12. Collect like terms and you get -2x plus 17. Here's an expression for f at x minus g at x. So if you wanted to do f at 6 minus g at 6, you could just sub 6 into this result instead of subbing 6 into both f and g and subtracting later on. F at x times g at x, well, this will kind of be interesting here. Notice we have a linear function and a linear function. Now, when we subtracted these two linear functions, we ended up with a linear function. What do you think is going to happen if we multiply these two linear functions? Well, let's take a look. We can multiply these expressions. So you're going to have to complete the multiplication for a binomial times a binomial. Sometimes we call that foiling. Anyway, when you do that expansion, you end up with these 4 terms here. And of course, you can collect like terms. We have minus 84x plus 45x. Put those together and we get the minus 39x. Now, what type of function is this? It's a parabola, and we know that because we have an x squared term here and an x term and a constant as well. So when we multiplied these two, we ended up with a parabola. These two lines multiplied to a parabola. And an interesting question to ask yourself is, will that always happen? If we multiply two linear functions, will we always get a quadratic function? And then you can look into other questions, like, for example, if we add two quadratic functions, will we always get a quadratic function? If you add two parabolas, is it always going to give us a parabola? And it really comes down to what the coefficients are in those equations. But I'll let you think about that. Let's do one more example here. In this one, we're given two graphs, a graph of function f and a graph of function g. That's f in red and g is in blue there. And we are going to sketch f plus g. Okay, now how do we do that? Well, first of all, notice that these two functions do have the same domain. That is all the real numbers from -5 up to 9. So their domains overlap completely here. So how do we add the functions? Well, you want to find some x values and then choose for each of those x values the two y values and add them together. Now, what do I mean choose? Well, you want to pick x values that allow you to easily read the y values. So for example, take a look right here. These are nice points to use because you can easily read the y values. So when x is -5, f has a value of 1, and g has a value of -3. Now 1 plus -3 is -2, so we can put a point at -2, still at an x value of -5. That's our sum right there. Now we want to find at least one more point where we can do that. And if you kind of look at all the points on these two graphs here, you'll notice at 7, we have something ideal happening. This point is right where the grid lines intersect, and so is this. So we can read those y values really easily. So we have that point there on f, we have that point there on g, and what are their y values? We have 5 on f, and we have -6 on g. So if you add 5 plus -6, you get -1, which is our point right there. Now, we're taking a line, or a segment of a line, that has a positive slope here and one that has a negative slope here, and we're adding them. What can we expect to get for our result? Well, remember that this line, I mean, if it was more than just the segment, it would have an equation of the form mx plus b. This line would also have an equation of the form mx plus b. And when you add those two together, would you get an equation of the form mx plus b? Well, based on what we see with our 2 points here, it looks like we're going to get a line, right? And that's going to happen. I mean, a couple things could happen. You can end up with an equation of the form mx plus b, or you could also get a cancellation of some of those terms. So you end up with perhaps something like y equals 5 or y equals 3x. Or something like that, depending on what the value of the y-intercept and slope are for each of these two lines. But in this case, we can see that line that we're going to get is going to be of the form mx plus b because it has a slope here. So we're expecting a line for this result, and we can actually just connect these 2 points to get that line. Because remember, we wanted to do f plus g. That means like for every single point, every single x value for f and g that are in the domains of f and g. Now, when you do connect these to show all those points, to show that resulting line segment, don't forget to keep going up till an x value of 9, because that's going right to the end of the domain for both of these functions. Right? So we want to make sure we get all of that in there. So we can draw it, and it looks something like this. There's f plus g, this line segment here. So we'll finish up with a couple of questions for discussion. Would the graph of f minus g look the same as the graph of g minus f? Well, we've kind of seen this before, and the answer is no. For example, if you did f minus g right here for this point, you'd get a value of 1 minus -3, which is 4. But if you did g minus f, you'd get -3 minus 1, which is -4. So the graphs are going to look different. All those y values or those result values that we're getting are going to have the opposite sign for each of these. That is, the y values for f minus g will have the opposite sign of those for g minus f. And what result would you expect to obtain if you were to sketch the graph of f times g? Well, we just saw something kind of like this too. We have a line, well, in this case, a line segment, but its equation would be something of the form mx plus b times another function whose equation is in the form mx plus b, y equals mx plus b. And when we multiply them, we'd be getting an x squared term, which means our result is going to be a parabola. Now, what that portion of a parabola looks like for these two functions, well, you'd have to go and multiply to see. For example, you might not see the vertex of the parabola. You might just see a curved segment or a curved part of the parabola, but that is actually part of a parabola because you're taking an mx plus b essentially times another mx plus b, which is going to give you, in this case, an x squared term. So it's going to be a part of a parabola. And that is really it, just a quick introduction to what it's all about when you're performing operations on functions. There you go.